Cleantech 101, Carbon Capture, Utilization and Storage. Why is carbon capture and storage important innovation for net zero? It removes global warming carbon dioxide emissions from the atmosphere. The carbon capture and utilization and storage system consists of three parts: the carbon capture itself, CO2 transport, and utilization or sequestration. First, it's worthwhile doing a quick overview of upstream oil production. Oil production is classified in three stages. Primary production, basically drilling a hole through the capstone and pumping the oil out due to the pressure of the reservoir. Then comes secondary production. Additional holes are drilled around the main well, and water is pumped down these holes to add pressure to the reservoir to pump even more oil out. Later in secondary production, superheated steam is pumped in to further aid the mobility of the oil within the reservoir. Regardless, even after primary and secondary extraction, usually 60 to 80% of the oil is still trapped in the porous bedrock. Finally, the most expensive stage, tertiary production, or more commonly called the science of enhanced oil recovery, or simply EOR. Rather than water, EOR introduces surfactant mixtures and solutions with high capillary reaction to squeeze out the oil from the interstitial cracks of the bedrock. One of the most popular methods of enhanced oil recovery is the use of liquid carbon dioxide. This is the principal irony that surrounds CCUS and the path to net zero. The very mature science behind it was originally developed to help extract out more oil. Indeed, increasing oil production is still the number one use of the means of disposal of CO2. As such, CCUS continues to be a major controversy in its classification in the world of green financing. So what happens to carbon dioxide pumped into reservoirs? The rock formations, which the CO2 is pumped into, used to hold highly pressurized natural gas under a non-porous rock layer. The CO2 will stay in its supercritical form for about 100 years while slowly being absorbed into the saline water, where it becomes more secure. Finally, a few hundred years later, the CO2 actually precipitates into the rock structure itself as solid carbonates and becomes permanently sequestered in the earth. Other storage options to sequester CO2 include simple saline aquifers. This is pretty much the same as the science of EOR, without any actual oil production, and hence no offsetting economic value add. There's also been examples of deep water canyon storage, kilometers under the ocean. However, I would personally classify these as experiments, as we are yet to fully understand the ecological impact. Other than burying the CO2, there are a number of ways of utilizing it. These could include fertilizer biomass production, catalytic conversion into products such as methanol, as well as ex situ trapping techniques where it's mixed in and mineralized with concrete and other building materials. Returning to the beginning of the system, how do we extract the carbon dioxide? The exhaust stream from a refinery or manufacturing facility that contains CO2 will be pushed through a solvent extraction column. An amine-based solvent then washes over the exhaust gas and extracts out the CO2. The CO2 amine mixture is then steam heated in an extractor, which separates the CO2 from the solvent. The concentrated CO2 stream is then compressed and cooled to produce liquid carbon dioxide, ready for piping or transport. There is certainly research underway for increasing the efficiency of solvent extraction and other novel techniques such as using activated membranes. There's even talk these days of extracting CO2 directly from the air. Finally, transport. The non-trivial volumes will require significant infrastructure in order to get the carbon sources to the carbon sinks.